A man of foresight, Honorable Dr. Patangrao Kadam Sahab established Bharati Vidyapit in 1964, the vision, social transformation through dynamic education. His dream came into the reality. In 1996, the Government of India granted status of university to Bharati Vidyapit.
Today, students from extremely diverse backgrounds are experiencing life transformation curricula in our college.
Curriculum here is purely industry oriented. Internship to the students, industrial training, involvement of the industry experts, guest lectures, live projects are integrated part of our curriculum. The day on which the student enter in this institute, we see that how he become industry ready by the time he graduates from this institute. Now we are going one step ahead and we are trying to make more and more entrepreneurs from this institute. In last 10 years, this institute has produced 1067 entrepreneurs. So practically 100 entrepreneurs per year. As a result of student performance, quality of teaching learning process, quality of faculty members, research, National Board of Accreditation has accredited our program in all its 3 cycles.
Bharati Vidyapit University ranked among top 100 universities of India by NIRF for consistently 3 years.
So we all departments together work for providing
project-based learning, digital transformation through innovation,
electronics for societal empowerment,
academic diligence, research prominence, industry consumption,
technological excellence for betterment of mankind,
pragmatic learning, societal projects and industry connect,
acquire technology zenith,
Manufacturing automation and management.
You dream it, we build it through functional excellence.
Activity-based learning of science.
Robotics and Automation, School of Nano Engineering, and School of Design are our future plans.
College of Engineering started a program in collaboration with Tata Consultancy Services, and in future we plan to start several programs in collaboration with multinationals.
Students here are very energetic and enthusiastic, and they have grabbed awards at various competitions in IITs, in IIMs, in cultural as well as sports competitions.
Our objective is not to create only employable graduates, but job creators also.
And this is the way we charge our students with dynamic education for their bright future.
Bharati Vidyapit University, College of Engineering, Pune, creating engineers for tomorrow.
There are so many college options, but I really want a college that will make me a good engineer, so that I can work on live projects and contribute as a good engineer of tomorrow.
A college that has latest equipment to learn through the experiments, giving me practical knowledge, but
where can I get such a college?
For all your needs, with latest laboratory facilities and equipments, where students conduct experiments,
Session will start within few minutes.
Hello. Good morning, sir.
प्रश्नाचे उत्तर मध्ये
Hello, sir. Please, first of all, unmute your mic, please. Hello.
कुणाला आवाजच जाणार
Yes. Thank you. Feedback bisa.
Hello. Yes, your screen is visible, sir.
आवाज इकडून टेस्ट कर.
Hello. Please unmute your mic, sir. Your screen is visible. 2 मिनिट चालू करा.
मला पण तिथलं झालंय चालेल बघूया.
Hello, good morning, everybody. Is the sound clear?
Yes, sir. Yes, sound is clear.
Sound is clear. Okay. Friends, very good morning and welcome all to this presentation. We will reserve all the questions to the
Sorry
end.
to interrupt you, sir. Just wait for few minutes. I will just give your introduction and we will start.
Okay. Thank you.
Very good afternoon to all. Hope you are doing well. I am Professor Akshay Araya. Welcome you for 5 days FDP on 5 days FDP on research opportunities in robotics automation organized by Department of Mechanical Engineering. For today's first session, we have with us Mr. Sunil Gokhale. He has completed his degree in electrical branch in 1982. Now he is working as the CEO of Awesome Technologies. He acquired knowledge of a wide range of subjects from field wiring, various sensors, SCADA, PLC system, and recently he is working on the IoT, that is the Internet of Things. He has completed more than 40 major projects in LabVIEW and application programming. After that, he has also worked on PLC application and programming and also microcontrollers and analog applications, which involves SCADA. Without taking much time, I welcome you, sir, on behalf of Bharati Vidyapeeth deemed to be University, College of Engineering, Pune. I request you to take the charge of the session and enlighten us with your warm words. Thank you.
Thank you, Professor. Friends, a very good morning and welcome all to this presentation. We will reserve the questions to the end of the session because we have a lot to cover. This talk is general and specific topics are not defined or highlighted, but each area that we talk about can be a topic for further research. Many aspects surrounding the subject need to be studied. And all the terms that I am using in this talk are used loosely to convey a concept and not defined rigidly. Okay, so with this introduction, let us dive into the subject. We will be covering the following topics today: the definition of robotics, robotics and automation, definition of automation, desired features of automation, human considerations and effects of automation, developments in automation and robotics, advanced access options, philosophical overview, ultimate robotics and automation, and requirements for research. Since we are going to be discussing on the research topics, we need to understand the requirements for research also. So that is the last topic that we are going to attack. Let's move on. Okay, let's come to the definition of robotics and automation. Automation is both, today it's prevalent in hardware as well as software. So let us define what automation is. Automation is, broadly speaking, substitution of human effort and intelligence by mechanized electrical, electronic machines, computers, and software. This is a broad definition. Automation, this word was coined during when Ford set up assembly line production for mass production of cars. This word was defined around that time. Examples of automation, many of us know what the examples are there, but we'll just list a few. Mechanized machines, automobiles, aeroplanes, harvesters, presses, electrical machines, we have motors, generators, microwave oven, mixer grinders, washing machines, etc. Electronic machines, we have weighing scales, digital cameras, calculators, photocopiers, robots. Computers, we have in avionics, satellite communication, advanced automation, internet bots, optical character recognition, web crawlers, etc. These are actually part of the software also. Software, we have robotic process automation, bots, crawlers, and viruses. Okay, these are some of the examples of automation. The need for robotics and automation. Why do we need robotics and automation today? Basically, to lower operating costs, improved worker safety. We have a lot of sensors provided in the automation system to prevent accidents. So this improves in turn worker safety. Reduce factory lead times. Since we know we have some consistency in production, we can predict and reduce the factory lead time for raw components as well as other sub-assemblies. Faster return on investment. Increase production output. Today, there is a highly competitive market. So whenever an opportunity arises, we need to capitalize on it as fast as possible. For that, we need increased production. So increased production output is one of the requirements. Then consistent improved productivity, quality, and efficiency. All these parameters are self-evident. Small environmental footprint. Now this arises from less wastage of material on the production floor. In automated systems, the wastage is less, but there are other repercussions which we will study later. But during the production, the material wastage is reduced to a minimum, which leads to a smaller environment footprint. Better planning and utilization of space. Robots and automation systems can operate in very, very compact space where humans cannot work. So utilization of space is better. Per square feet, the production is more in an automated environment than in a purely human or manual environment. Reduce need for outsourcing. If we have automated systems, we can develop products in-house, we can do tooling in-house, we can do prototyping in-house. Yes. I was getting some feedback, audio feedback. Anyway, reduce need for outsourcing. Okay. This actually today is becoming a major thing. USA is trying to reduce its dependence on China for manufacturing. And the only way they can do and shift production back to USA is with use of robotics and automation. Earlier, they had migrated their work to China because of cheap labor, loose norms. So these were the main factors. Shortage of labor in the US, but with automation and robotics, they can shift the production back to USA. So reduce the need for outsourcing. Adaptability and reconfigurability. Today, a company produces maybe 10 products. The same production line can be reconfigured just by uploading a new recipe and the production will be set up for a new product. Adaptability is using the same machine with different tools, maybe like a tool turret of a CNC machine, where the turret operation is the same, but it can pick up a milling tool or a grinding tool or drilling tool. So adaptability, or in a robo, for example, you can have different types of grippers for different products. So adapting the system is one of the requirements for robotics and automation. So these essentially are the reasons why we would go for robotics and automation. Software or hardware. Today, in earlier days, robotics and automation was purely hardware. But today we find there are software robots. We'll look at some of them. Robots and automation can be software or hardware. Hardware, we have production machines, pick and place robots, painting and welding robots, robots that operate in mines, in nuclear facilities, search and rescue operations, autonomous vehicles, smartphones, etc. There are hundreds of applications that you will find today. Practically everywhere we have microcontroller-based, computer-based automated systems. Even in a house, we use around 50 microcontrollers, if I'm not mistaken. Software, we have something called bots, which is short for robot. They are also called web crawlers. Viruses are also a part of automation. They are automated robots designed for a particular work. Of course, office automation is there. Document management system, which has become a big thing today for knowledge process outsourcing, or knowledge office, whatever you call it. The document management system is becoming very important. And of course, robotic process automation. Robotic process automation are small programs which have been designed to automate certain tasks in corporations. We'll come to that later. We'll discuss that a little bit later. So we'll take up the software robots first. Software robots. Bots, botnets, crawlet on spiders. Bots is a short form, like I said, for robots. Botnet basically is a network of these bots, okay, which crawl the net. So they were also called crawlers and spiders. These bots, they spread over the internet, and they were basically used for indexing by search engines. Google uses them extensively. These software bots, they crawl the web looking for search engines, looking at the DNS registry, that is the domain name service, from where the web pages are. It's a basically DNS is a library of web pages. So they pick up each site name from the DNS, and they go to that site and they catalog the keywords. These automated bots, they are used for indexing by search engines. There are some web pages which are not text-based. They are pictures. They are basically text, but captured in the form of a picture, and they cannot be read as text. So we have optical character recognition for such web pages. So Google uses OCR also for web page scanning. Then there are bots which do auto login. They crack the password. I believe about 70 to 80% of passwords today are very, very common type, which can be easily cracked. So these bots, they log into the system by cracking some password, and they surf on your behalf, or they surf to find further data, what the thing is about. That is why today banks have introduced something called CAPTCHA. If you do net banking, we must have seen every bank page today, net banking page, asks you for CAPTCHA or an image. The reason being, they want to block this optical character recognition and search engines from logging in, auto logging in into your system and playing a havoc. So CAPTCHAs basically are words which cannot be read easily. Optical character recognition, you require some cognitive abilities to read them. Also, there are pictures where you have to find certain things, maybe ships or bikes or pedestrian crossings. You have a set of images from which you have to select images which pertain to a particular object. So these are basically mechanisms to defeat optical character recognition of these bots. Okay. So in practical applications, we use this today. Banks have made it mandatory to use CAPTCHA now. Also, after indexing, there are hundreds of thousands of websites which are filtered using keywords, but not all of them may be relevant. The most relevant websites to you are presented to you by using artificial intelligence. Google uses this extensively to provide you with absolutely relevant web pages and websites. So these are software bots and crawlers. Then we have viruses, which are also robots. These are programs designed for espionage, destruction, or backdoor access into systems. In fact, if you read the story, the Iran's nuclear program basically was killed by a backdoor entry, a virus which was provided into the system by a different country. We'll not get into the names of the countries, but there was a backdoor entry which was created using viruses, and they used this to access the systems and kill the Iran's nuclear program. Okay, then we have robotic process automation. Robotic process automation is nothing but manual processes on computers which are done by humans. They are automated and a small program is created which runs autonomously. It can run by itself or you can schedule to run it at a particular time. So this is basically robotic process automation. For example, these are the softwares which provide you with robotic process automation. Blue Prism is one product. UiPath is another product. Here, basically, for example, Bank Mega Indonesia, they could increase their production and reduce interaction time with the customers by using robotic process automation. Customers used to call them for either some problem or some password change or email access to something, or their password needed to be changed, or they have forgotten their password. So for such operations, a lot of human effort was required, and which delayed interaction with the system. So Bank Mega Indonesia adopted one of these packages. I believe it is the Blue Prism or UiPath, and automated these processes. So today, the waiting time for password change has gone down from 6 to 10 hours to 5 minutes. Similarly, credit card applications processing, which required more than 24 hours, has been brought down to 5 minutes by robotic process automation. So these things like credit card application processing, password authentication change, or credit limit change, or accessing a loan, these processes have been automated using robotic process automation. Currently, Bank Mega Indonesia, 30 processes have been automated, and some 200 more are lined up for future. Second example is of biggest bank in Korea, which is KB Kumin Bank, which believes in agile organization to quickly adapt to circumstances and provide the best service in the market. They want to be very competitive in the market in their services, bank services, and they have automated around 183 processes till date. Also, one of the points to be considered for robotic process automation is some of the softwares require specialist engineers or software engineers to configure the system. But there is a trend to move to citizen developer model, what is called a citizen developer model, where the end user himself can design, automate his own process. So this is also another area for research where you can bring in ease of use for the user to programming. User experience, and this is the part which I was referring to, user experience and user interface design. As the systems today become more complex, whether they are hardware systems or software systems, we can take the example of autonomous car or today Tesla Model T. The interaction with the system today needs to be very fast, very clear, and easy to use. The touchscreen displays and the connected devices form the basis of user experience and user interface design. So this is another area of research. Designing chatbots on websites, basically to bring ease of use to the customer. So this is all about software robotics. minimalistic design. Yeah, designing simple screens is very important uh, for a user to use the system effectively. Too much of complexity, too much of complex setting on the system can confuse the user, and he will not be able to use the system optimally. So minimalistic design is also very important. So this is all about software, robotics, and automation. Now let's move on to conventional. Whenever we talk of robotics and automation, it is generally with respect to manufacturing and production processes. So let me give you an overview on basic hardware evolution of the hardware evolution in robotics and automation. Okay, when automation started, maybe in the 60s or early 70s, they used something called as relay logic. The relay contacts were used for and or operations, which defined the logic for the system and the sequencing of operations. Okay, but relays inherently have many problems. They had their limitations. Being mechanical devices, they failed after a certain number of operations. They were difficult and expensive to modify, difficult to troubleshoot, because once something trips, the whole system trips. So you don't know where exactly the fault occurred. So they've become very difficult to troubleshoot. They required frequent maintenance. In fact, we had a company in Thane, Windsor, which manufactured molding machines. And in their machines, when they use relay logic, they used to tell their service technicians first thing to go and pour IPA onto the relay panel. They switch off the system and they used to wash the relays with IPA, and that is isopropyl alcohol, to remove all carbon from the contacts of these relay contacts. These carbon deposits which were there caused erratic operation, and it was impossible or very, very difficult to diagnose the fault in the system. So one of the first things they used to do is wash the entire system with RBA and remove all the carbon which created shorts. Okay, so relays had their problem. This was replaced subsequently by hardware gate blocks. Initially, relay contacts were used for AND gate, OR gate, NOT gate, these kind of wirings, set, reset, elements. This kind of logic, relay logic, was implemented. Later on, there were hardware blocks, AND gate, like AND gate ICs, basically designed for industrial use. So Siemens had AND gate blocks. That system was called Simatic C1, and it had AND gate blocks, OR gate blocks, NOT blocks, timer blocks. These kind of, but these systems were definitely much more reliable than the relay logic. And I have seen a system in 82, 83, when I went to JK Synthetics. They had a system using this relay blocks, these hardware gate blocks, which they had installed in 1968. So from 68 to 82, this system was working absolutely fine. But this also required extensive maintenance, and the wiring was huge. Since we are using gates, individual gates for logic, the panels were big, there was extensive wiring, and unless you had a proper diagram, it was difficult to diagnose these systems. Just after this relay blocks went out of use, we had discrete CPUs. When I joined Siemens in 1982, Siemens had just introduced the 110A system. 110A was one of the first PLCs from Siemens, and this was made using discrete CPU. Discrete CPU in the sense it did not have any microprocessor or microcontroller. The entire CPU was made using gates and counters and the resistors. If people here have gone through Malvino books, which was one of the most popular authors during our college time, beautiful books written by Albert Paul Malvino. One of his first books, called Digital Computer Fundamentals. In that book, he had developed 3 CPUs, SAP 1, SAP 2, and SAP 3. SAP stands for simple as possible. Those CPUs were designed using gates. So this Siemens 110A CPU was something similar to that. It was designed using gates, shift registers, and clocks. So Siemens 110A was one of the first PLC systems where a CPU was designed, and it used separate hardware, timers, and counter module. Timers and counters were not there in software. Since the CPU itself did not have any memory or anything, it was just built with gates. There was no memory inside it, so there were no timer and counters in it. Next came the first microprocessor-based PLCs, 110S and 150S, but these had separate communication modules with custom displays and keyboards. 110S system used 8085 microprocessor rather, and 150S that time used something called as a bit slice processor. AMD was one of the first companies in the world to come out with a bit slice processor, the AMD 2901. This processor was a 4-bit processor, and Siemens had used 4 of them in parallel to make a 16-bit processor. So this 150S system of Siemens used that kind of processor, but it had external communication modules with custom displays and keyboards. By the way, we were manufacturing keyboards for Siemens for this particular system. This was subsequently, after the microprocessor-based systems, came the microcontroller-based CPUs with integrated communication interfaces like RS232C, RS485, and the display and keyboard interfaces were replaced by PC-based HMI, SCADA, and also simple robots came into being. Okay, communication interface RS232C we know today it's a serial interface. RS485 also is a serial interface. PC-based HMI is human-machine interface, interacting, feeding, changing the timer values, adding recipes to the system. All this was done using SCADA and HMI. And simple robots, mechanical robots, pneumatic robots came into being that time. Then came PC-based CPUs. PC-based CPUs basically is actual PC cards put into being used as CPUs. There are 2 well-known companies today which are using this. One is National Instruments. I'm sure many of you must have used LabVIEW software from National Instruments. National Instruments make a system called Cerio, that is compact Rio. This compact Rio CPUs are basically complete PCs. They are 486 based, 586 based PCs with all kinds of interfaces, Ethernet, Wi-Fi, mobile, everything is built into the CPU itself. Similarly, there's another company called Beckhoff Automation, which is from Germany. They also make CPUs which are basically PCs. They are 486 based, Pentium based, and today I believe they are multi-core CPUs also available. So PCs themselves have become CPUs in PLC systems in automation today. Also, the robots evolved. They became advanced pick and place systems. We have advanced pick and place systems. We have welding robots today, which perform a very critical job in automobiles especially. We have painting robots. Again, painting process is one of the most important processes in automobile industry. And they were fixed, but these robots were fixed with a fixed working envelope. An envelope is an area in which a robot can work. The maximum extension of the arm of the robot or the area which the robot can access is called its working envelope. So robots were fixed robots with a fixed working envelope earlier. Today we have mobile robots. Example being automatic trolleys which carry parts from storage to production line when required, that is just in time. Or today, if you look at any automobile industry, we have why use automobile industry as a reference? because automobile industry uses the maximum automation today. Okay, most of the production lines of BMW, Rolls-Royce, Volkswagen, and all these companies, including Maruti and Tata Motors, they are using robots for their production system. And we have mobile robots today, which bring parts, which carry parts from the storage to production line when it is just required. And these robots are very cognitive in the sense they are aware of the surroundings. They can sense human presence. They stop when required, and they manage to bring parts in time. They manage themselves to bring parts absolutely on time. So the robots are from fixed robots, they have become mobile robots now. Next came the interactive robots with haptic feedback used in surgery. Now, what is haptic feedback? Haptic feedback is a click when you press a key. That mechanical feedback that you get by pressing a key is called a haptic feedback. Today, you must have noticed in mobile phones, when we click a picture, there is a click sound which comes. Now, this click sound is not coming from mechanical. In olden cameras, that sound was actually the camera of shutter clicking. But in to give you the same experience in mobile phones, the click sound is generated through a speaker. There is no actual sound of the shutter. Now, this kind of sound feedback is called a haptic feedback. You get the feeling of something mechanical when it is not present actually. Okay. Now, in the interactive robots, basically surgery robots today, what are the surgery robots? Surgery robots are robots where, for example, at Kokila Bain Hospital today, we have a robotic surgery unit they have recently set up. So there is a robot there, and if you have a patient who needs a surgery, a particular type of surgery, and the doctor is not available locally, but he happens to be sitting in the US. So this robot actually performs the surgery the way the surgeon performs it in US. So the patient is in Mumbai, the surgeon is in maybe New York. He actually performs the surgery from there. His hand movements, his actions are replicated here by robots in real time. And not only they do perform operations in real time, they also provide feedback to the surgeon. For example, when you cut the skin of a patient, there is some resistance. There's some resistance is felt when you actually cut through a skin. So that feedback is sent back to the surgeon, and the surgeon actually feels that he's cutting through a skin. So this is a haptic feedback which is provided. Now, these are the most advanced robots that we are having in this country today. And there are a couple of hospitals who have already set up robotic surgery in India today. This is where the robots are moving to. Further, we come to thought control systems. Today, thought control systems are on experimental in experimental phase right now, but they are being used for fighter pilots, the head-up displays of fighter pilots. Planes have become so fast. The fighter planes today are traveling at Mach 2 and Mach 3. The reaction time is so slow. You don't have much time to react. And there are such advanced controls available that pressing buttons is not an option today. So we are slowly moving towards thought control systems. Okay. These thought control systems are also used for disabled people who are not able to move their limbs. So when they are fitted with artificial limbs, they can move these limbs with thoughts. So these are some advanced thought control applications. This is a very good area for research. Of course, autonomous systems. Suppose you have a disabled driver. Now we knew one of the most famous disabled persons in this world was Professor Dr. Stephen Hawking, who was the Lucasian professor of mathematics, as we all know. He was completely disabled. The only thing he could move was his eyelids and nothing else. Just by his lips and eyes, he could type words into a system. So thought control system, of course, it was not thought control, but we can evolve to thought control. His brain was functioning perfectly till the end. So thought control systems could help such people also. Now we've discussed the hardware evolution of the PLCs and software. Let us go on to desired features in robotics and automation. What do you want from such systems? You want configurability, of course, because the same production line must be capable of producing different products. In fact, there is a company in Hyderabad, if I'm not mistaken, which is manufacturing mobile phones for different companies. So the same company is manufacturing products for, I believe, OnePlus. They are manufacturing for Xiaomi and other companies. So the same production line is used to configured for different products. So configurability is one of the key factors. Adaptability, like I said, using the same system with different grippers, different tools, we can adapt it to different functionality. So adaptability is also important. This can help in reducing costs. Networks and communications is absolutely important. Today, most of the production lines, we have subsystems cascaded together. We have station 1, station 2, station 3, station 4, and multiple stations in a production line. To synchronize the workflow or the production flow, we need proper network and communication between the systems. So network and communication is a very, very desirable feature for robotics and automation. Cognitive abilities are basically sensing the environment and making decisions. Okay. Earlier, the robotics were mechanical, sort of mechanical devices. They are programmed to do fixed tasks. They would just move in a particular way and do their fixed things. But today, we need cognitive abilities. Like for mobile robots, they can sense presence of humans to avoid accidents. If there is a change in system, they can change their behavior slightly to adapt to the changes in the system. So these are some cognitive abilities. You can have vision, you can have decision making, you can have sound recognition. So cognitive abilities is a desired feature in automation. Cooperative. Cooperative in the sense, like I said, we have multiple stations and one subsystem has to cooperate with the system in front and the system behind to synchronize the workflow. So cooperative robots is the ability to adapt to and synchronize the workflow and optimize it. Collaborative robots or automation. Let us say we have a product which has 5 stages, and stage number 3 requires most time, but stages 1, 2, and 4, 5 require less time. So the entire manufacturing time is determined by station 3, which requires the most time. But suppose we are able to put 3 station 3s in parallel and bring down the time, then you can achieve greater production. For this to happen, all the station 3 systems have to collaborate with each other. So cooperative is slightly different, collaborating is slightly different. So these 3 systems, they talk to each other and they manage to feed the product to the next station in the correct time. So these are collaborative. Also collaborative systems are used in Internet of Things. Today, basically, unfortunately, these technologies are being used for warfare, where hundreds of robots are released at a time. And these robots, they collaborate among themselves. They identify a target, they share a target, they say, okay, I've got this target, you take another one. So that kind of collaboration is being done. So these are the desired features, okay, of robotics and automation. Human considerations. As robots become complex and interact with humans, there are chances of accident. Accidentally, many times what happens is a human on a production floor sees something wrong and immediately bends down to pick it up. When that happens, he moves into the envelope of a robot and accidents can happen. To prevent such accidents, robots must be human aware and must adapt to change in the human behavior. So this is one of the requirements, human consideration. Ironies of automation. Irony, why irony? Because it is a general belief that automation reduces workload on humans. Practically, it has been observed that it is not so. The workload is shifted, and the workload may actually increase for operators. The operators need to be more alert, more decision making, more cognitive, and they have to take decisions extremely fast. So, uneven distribution of load there. Increasing load may be more of, see, when you do automation, and for a new operator, the change in load on him is very high compared to a person who's familiar with automation. So there's an uneven distribution of load. Also, if you take the case of a pilot, most of the time when he's on course and is flying straight, the system is on autopilot and everything works fine. But when it comes to landing and takeoff, the load on the pilot increases disproportionately because now he has to take command from the ATC, which is the air traffic controller. He has to take command from the ATC and feed correct information into the system. So he not only has to talk to the ATC, he has to also manage the system differently, and that too in a very short time when during takeoff and landing. So the distribution of load is uneven completely. There is no load while cruising on a particular altitude and the course is set, but during takeoff and landing, the load may increase disproportionately. Okay. New attentional and knowledge demand. Now, attentional in the sense, since we have robots which are working very fast, the production time is reduced, the systems are moving like a fighter pilot, like I said. The systems have become so fast, the speed has increased so much, the attention requirement on a pilot or an operator are very, very high. Even for an autonomous driving system or a pilot operated system, the attention to detail is very, very high. We need to pay attention to because reaction times, the system is moving much, much faster than what human can do. So if there is something wrong, the correction time also is very, very small. So you need extreme attention while using such systems. Also, the knowledge demands on the systems are increased because now we need to understand the relationship between inputs and outputs of a system. The reaction time when an input is given till the output is generated, these reaction lags also can create a problem sometimes. We see this more often with softwares, especially .NET software. You do something on the screen and it takes a while for it to change. Okay, so .NET software basically are lagging. So similar things happen in real-time systems also. Whenever an operator feeds an input, or let's say he puts a brake, presses the brake pedal, the system to stop might take certain time. This time actually theoretically should be zero, but practically it takes a certain amount of milliseconds. So while you are driving on roads, braking of a system, you need to have the knowledge of how fast it is going to react, how it is going to react. So the knowledge demands have increased. There is a demand for cognitive abilities also. Decision making based on information, prior knowledge and inference. Cognition basically is making decisions based on information, prior knowledge and conclusions that you can draw. So these abilities have also increased. Use, misuse, disuse and abuse of automation. Use basically refers to voluntary activation or disactivation of automation by operators. There are certain features which are deliberately defeated sometimes because they create additional delays. typical in molding machines, molding machines basically have a safety door in front. There is a die which presses, closes. During the closing operation of the die, the door needs to be closed to prevent any object being smashed by the molds. Okay. So, but what these operators do many times, I have seen, observed in the industry, they defeat the safety mechanism. They remove the glass from the safety door, or they'll tie up the safety limit switch with a rope and close the switch. Keep the gate open, but they close the switch using a rope or some cable tie. So this is basically misuse of system. The system is there to prevent accidents, but that delay of opening and closing the door, they want to take off. Even that. So basically, misuse refers to this kind of things. I have seen. In fact, there was an accident which happened on a night shift. It was a Windsor machine, and this operator had removed the safety door, the glass on the safety door. The door was closed, but the glass was removed. So he could directly put his hand in and remove the object from the mold. During the night shift, what these operators generally do is they increase the production by defeating safety, and whatever time they save, they used to sleep on duty. They use it for sleeping. So in that kind of a state, this operator put his hand into the system when the safety door was locked, and his hand got smashed, crushed in the mold. So these kind of accidents can happen with misuse of the system. Disuse is basically underutilization of automation. You don't use it to the full extent. The system is capable of producing a lot more, but you don't use it to the full extent because you have defeated certain operations in it. And abuse is like what I told you, defeating safety. As a misuse of automation is basically, see, many times what happens is the system is not programmed completely or properly. It generates false alarms. So people over time realize that this is a false alarm and there is nothing wrong with the system actually. And they continue using the system by defeating that particular alarm. Now, this is actually a misuse of the system. I had seen one case when I was flying, I believe, to Bangalore once. I happened to know the pilot. So I just peeked into the cockpit and on his screen, on the instrument panel in front of him, I kept seeing one particular alarm which said fuel pump failure. So I asked this pilot, I said, if this is a fuel pump failure, how come you're flying this aircraft? He's saying, no, that sensor is faulty. There is nothing wrong with the fuel pump. That sensor is faulty. We have not had time to change that fuel pump, this sensor. So we have defeated the system and we are continuing to use it. So this, if you know what is there, but suppose the next pilot who comes, who takes the flight, let us say from Bangalore to Trivandrum, he doesn't know this, that there is nothing wrong with the fuel pump. He might refuse to fly or he might take decisions which are detrimental to the operation. So this defeating or not correcting problems in the system is misuse of the automation. Trust in automation. This is also one of the very, very important factors when you think of automation and robotics. I'll give you an example. Suppose the system tells you that there is some danger and you need to take this action. Will you take the action or will you not take the action? That depends on how much trust you have in the system. I'll tell you a classic case. Earlier, there are a lot of mid-air collisions in aircraft. Okay, due to wrong understanding. In fact, we had one of the accidents near Delhi airport when a Kazakhstan Airways and some other plane, one was coming into land, the other was going for taking off from Delhi. Now there is these pilots are undergo language training every 6 months. Okay. Now there is a typical way in which the air traffic controller and the pilots refer to altitude. At least they did in those old days. I don't know if they changed the system now. In these old days, they used to drop the last two zeros of the altitude. So when you said 50, it meant 5,000. When you said 250, it meant 25,000. Now, what happened was, there was this Kazakhstan airway which was coming in to land, and it was at an altitude of 6,000 feet. And there was another aircraft which took off from Delhi airport, and he was ordered by the ATC to go to 5,000 feet. So he wanted to maintain 1,000 feet gap between the incoming aircraft and the outgoing aircraft. Now, because they had this habit of dropping the last two zeros, what happened was the ATC gave instruction to the outgoing aircraft, clear to 50. What he meant was clear to 50. That means clear to 5,000. You go up to 5,000 feet. The pilot, instead of clear going to 5,000 feet, he took it as clear to 50, means 25,000 feet. He was under the impression there is nobody coming in and I am free to climb right up 25,000 feet. So he started climbing desperately, and this aircraft, which was at 6,000 feet, which was coming into land, he went and banged into it, and a major accident happened. If you remember, this debris was found in Ambala, Punjab fields and all that. And of course, everybody was in the accident was killed. But to prevent such kind of accidents, the aircraft has introduced something called as TCAS, Traffic Collision Avoidance System, which is used in aircraft. Okay. But there was another case where two airplanes in Europe were flying towards each other, and both the aircraft were fitted with TCAS, Traffic Collision Avoidance System. What TCAS does is, it makes an instant decision based on the current altitudes of the planes. It tells one aircraft to start climbing, and it tells the other aircraft to start descending. To avoid the accident, this TCAS, the radars check the aircraft radars check the proximity of other aircraft, and if they are on the same course, the TCAS basically tells one aircraft to climb and it tells the other aircraft to go low. But one of the pilots didn't have trust in the system. He trusted his own judgment rather than he trust in the system. And he also decided to climb. The other pilot followed the TCAS instruction and he started climbing. This person, he also decided, he said, TCAS is telling me to go down, but he said down there could be a problem, so I'm going to climb up. So he also started climbing up, and this guy also climbed up, and they had a mirror collision there. That was because one pilot did not trust the system. Today, there is a standard instruction by National Air Traffic Board, NTSB, National Travel Safety Board, that you must listen to TCAS. Whatever TCAS says, you have to do immediately. So trust in automation, which also is an important factor and consideration. Situational awareness. Situational awareness is going beyond our normal sense of duty to find the envelope of operation. What does it mean? Basically, we'll again take the case of automation in aviation. It basically means perception of elements. Situational awareness is basically perception of every element within a volume of time and space, understanding their meaning and projecting their effect in the near future. It means perceiving and understanding of critical factors, their effect on my current goal, okay, and also understanding at a high level, seeing that what will be the effect in say a little distant future if I do this, or if something like this happens, what is going to be the effect maybe 10 minutes down the line, half an hour down the line. Now this we'll take the example of aircraft environment. Basically, the pilot needs to understand, before taking off, he needs to understand the flight parameters, the flight goal, the destination, the condition and status of onboard automation systems, Like I told you, I gave you the example of the fuel pump not working. If the pilot must be aware that the fuel pump is okay, but the sensor is faulty. He needs to understand the status of automation of his system. So situational awareness means all this. You should know the aircraft parameters, the flight goal, the condition and status of onboard automation system, their own position when you're flying through the sky. You must be aware roughly in which part of the world you are flying right now. What is your geographical location currently, irrespective of the system. This you can assess from visual landmarks. Okay, not relying entirely on the system. You can assess the situation from the terrain reference or some visible landmarks which are there, which you can see. Flight path awareness. You should know on this flight, generally at this time, how many aircraft would be flying, how many would be coming towards you, how many will be going in the same direction as you, roughly. So this information is all beneficial when you need to make decisions. Sometimes you have to take a bigger picture, look at the bigger picture. So overall view and understanding of the system is critical to decision making in challenging time. So this is basically called as situational awareness. Besides your actual system which you are controlling, we also need to understand what external parameters can influence the system while we are using it. So this is called situational awareness. So these are some of the considerations. These by no means are all the considerations. There are hundreds of things that you can come to. Each of these areas are research areas actually. Developments in robotics and automation. So developments in robotics and automation, basically we have artificial intelligence and neural networks now coming in. Artificial intelligence neural network, for example, in autonomous driving system, we have a 360-degree vision of around the vehicle. Today, even in our Skoda cars which are available in India, if you've driven in a Skoda Octavia today, you'll find there are sensors all around the body, and whenever you're in a traffic, if any vehicle comes within 1 feet of you, the dashboard starts beeping and tells you in which direction the object is in close proximity. So we have artificial intelligence decision making, especially important for autonomous vehicles. Sensing the speed of vehicle in front, sensing the speed of the vehicle behind, controlling the brakes, or maybe overtaking, ABS systems. So all these are part of modern robotics and automation. Autonomous planes. In fact, day before yesterday, I got a video on WhatsApp of an F-16 flying itself. The pilot actually not flying itself. The pilot was on the ground, but a F-15, he was flying an F-15 sitting in a room on the ground near the airport. So these systems, it is using the pilot's intelligence. Also, there is certain intelligence built into the aircraft for self-preservation and avoidance of danger. So we have these artificial and neural networks which are coming in. These are also available. These are also coming in a big way in software for business intelligence, business decision making. You have software like HANA in SAP, or you have SAS, which are basically neural networks and big data processing. All these are artificial intelligence based. Exoskeletons and intelligent body armor. Exoskeletons are basically robots which you fit to your body. These actually can help you in many ways. Especially for disabled people. Robots, exoskeletons which are fitted to their body can help them walk. People who are paralyzed, who are not able to walk without a walker or support, can use exoskeletons to walk. Also, if your vision is impaired, you can have night vision or you can have day vision, especially soldiers who are working on the border. today use these exoskeletons, which contain night vision systems, targeting system, laser systems, which are all built into the body armor. We can have systems. In fact, there is research going on body armors where our soldier becomes instantly invisible. Basically, the clothing is made up of flexible screens, and the flexible screen, there are cameras which pick up the surrounding and project the same scene on the skin, which is nothing but a screen, a soft screen, and the person becomes invisible because the screen displays the same background against which he is standing. So the person, you cannot distinguish the person. So intelligent body armors are also becoming are advances in robotics basically. Exoskeleton, people who are not able to walk, or even people who are able to walk, but let us say he's a firefighter, and you're a firefighter and accident like 9/11 happens. He has to walk up. Now, whenever such a fire happens, first thing they do is they shut down the electrical system to prevent further accident. Now, if the electrical system is shut down, a person may have to walk 40 floors or 50 floors or 100 floors up, especially in skyscrapers. Now, if you have exoskeletons fitted to your body, which are robots, which increase your strength, for the effort, we only need to direct the robo, and the robo does the job of walking. People are able to climb 100 floors without getting tired by using exoskeletons. Okay, experiments are being done in Japan to help disabled patients to start walking around, walking again. These exoskeletons can also help improve your vision. They can improve your hearing. And of course, they are used in warfare and other pieces. Surgical robots. Surgical robots is what I mentioned before. Basically, robots which are used for performing surgery. The patient is under one robo, and there is a similar robo sitting somewhere else in the world where the doctor is performing the operation. Whatever movements the doctor performs on that robo, the same motions are replicated by this robo here, and the robo also sends him real-time feedback on what is happening. So these are surgical robots where you need tremendous sensitivity, fantastic sensors, fast communication. In fact, whatever hand movement the surgeon performs, the same movement must be performed by this robo almost instantaneously. So there is no lag for the surgeon. And the surgeon gets a real experience of performing operation on a real body. So surgical robots demand the maximum and the best that is there in automation today. We have cobots. Cobots basically a cooperative robot. Cooperative robot, you can improve the efficiency of systems by humans and robots working together. But if humans and robots are working together, there are chances of accidents, mishaps. So the robots must be cognitive or cooperative. Also, they must interact with the system before them, and they must interact with the system after them. So cooperative robots, basically they cooperate to maintain the smooth flow, production flow, and also are human aware to prevent accidents. So these are basically cobots. Network collaborative robots. Collaborative robots, like I said, are robot working in parallel. I'll give you an example. I had seen one video on WhatsApp where each bullet was basically a flying machine. It's a tiny robot. Each bullet was given a wing. It was made into an airplane. And hundreds and thousands of such bullets were released into the air. Now these bullets would swarm a building or a city. Okay. They can go through windows, tiny crevices, tiny openings, because these robots were so small, they could fit, you could fit 5 or 10 of them in your hand. They are so tiny, and each robo was basically a bullet. So what this did was, I mean, this is what was shown in the video. I'm not sure whether it's real or no, but there are good chances that it's real. These bullets would swarm into a building through any opening that is available, would find out humans, would detect humans, and go and bang into the forehead and kill that person instantaneously. Now these robots, now there is so much decision making to happen. Let us say there are 15 people in the room and there are some 25 robots which swarm into the building. Now wasting resources is not an option. It can happen that 2 bullets can target the same person, or maybe one person is not targeted at all. So such thing, for such decision making, you require collaborative robots. You need robots which can fly, first of all, avoid obstacles. You need robots which can detect a human. Not only once a human is detected and targeted, it has to inform its other neighbors that I have selected this particular person, you don't select it. Okay, so this was a fantastic example of collaborative robots which I've seen. Of course, it was meant for a destructive use, but this was a network collaborative robot. This is an example of network collaborative robot which I had seen. Advanced access option, like I said, thought processes. Here I would like to mention there was one experiment conducted in Georgia Tech Institute long time back. This is mentioned in Deepak Chopra's book, The Perfect Health, where he says an experiment was conducted in Georgia Tech Institute. There was a computer which was asked to toss a coin. Okay, binary 1 or 0. It was asked to toss a coin, heads or tails. Now, as we know, probability theory says if you have millions of tries, the probability of heads or the probability of tails is equal. Okay, so 50% of the time you'd get 1, 50% of the time you'd get 0. And computer being computer, it can throw the dice millions of times in a few seconds. So this computer was programmed to do that, and it was continuously tossing a coin and generating 1, 0, heads or tails, or ones or zeros. It was generated, and as expected, the probability of ones and zeros was 50%, very, very close to 50%. Now what they did was they put a human being in front of the computer. That human being, he's not supposed to touch the keyboard. He's not supposed to touch anything in the system. He's not supposed to talk to the system or anything. There was no voice. There was no voice activated command. Okay. Now this person, all he was to do was think 1 or think 0 continuously. All he has to do is concentrate and think 1 or think 0. So this person sat in front of the computer and he thought about 1, 1, 1, 1, 1, 1, 1 all the time. And they found that the probability shifted towards 1 by more than 15%. Okay. Now he's not touching the computer. He's not interacting the computer with anything. He's only thinking. He's only thinking. And the probability shifted towards 1 by more than 15%. Similarly, when he was asked to think about 0, the probability shifted towards 0 by more than 15%. Now, how did this happen? He's not touching the system. Okay, so this was very surprising, they discovered. Based on this, there is a project which is currently going on, which is live right now. People, you can check it out on Google. A project called Global Consciousness Project. A Global Consciousness Project is set up by Harvard University. Basically, what it is Global Consciousness Project is a set of computers, or I think 72 or 144 or 192, I don't know what is the latest number, but it is a network of computers scattered all over the world, in different places in the world. And these computers are generating random numbers. Okay, nobody is interacting with these computers. Nobody is doing anything to them. They are just generating random numbers. Now, whenever you take a sum of these random numbers, as expected, the line is a flat line. Okay. In normal circumstances, the result of the summation or whatever processing they do on these numbers, the result is a flat line. When 9/11 happened, somebody thought of this experiment. This experiment was already put into place, and they wanted to see what, if any, there was any effect from this system. So the first plane that hit that tower in 9/11 was around 8:15 or 8:20 or something like that in the morning. It was after 8 o'clock in the morning. But when they studied the results of this global consciousness project system, they found the graph had started going up at 5 o'clock in the morning, long before the actual incident took place. The graph was started going up, which normally remains flat. The graph had started going up at 5 o'clock in the morning. Then they checked the results for some other global calamities. Whenever a major earthquake happened, or whenever any other war happened, or any other major incident happened, they found the system going in one direction. Now, how is it this possible? So there is some weird thing which is happening. Now, these are all dumb systems, supposed to be dumb systems. Nobody is controlling them, yet these systems are giving these kind of results. So advanced access options today, maybe tomorrow you can control various systems using just by a thought process. Already heads-up displays and some other displays are being tried in fighter aircraft to use this kind of options, advanced options. Okay, so it's a very, very interesting thing which is happening in the world, access. Okay, philosophy. Now we come to a slightly different aspect which also needs to be researched. Automation basically has led to a couple of problems. One is problem of overproduction. Second is problem of waste. See, because there is overproduction and companies want to continue running their businesses, what has happened is the products don't last. They make products not to last for more than 2 or 3 years. The product design is such, either the features are increased or the product is made redundant by deliberate design. Okay, so that they can continue to produce. But because of this, there is also a lot of amount of waste which is generated. Okay, because there is an overproduction, since the production must be put to use and the factories must be kept running, the previously produced products have to be discarded. And this has led to a lot of waste. Today we know e-waste has become a big challenge. Plastic waste has become a big challenge. So it has also led to generation of waste, which is difficult. So way back in 1973, there was a book written by Dr. E.F. Schumacher, who was the United Nations Economic Advisor, and he has written a very beautiful book called Small is Beautiful. And in this book, he asks a fundamental question. Would you call any business destroying its own capital as profitable? Now we all know, common sense tells us that if you are destroying your capital, the business cannot be profitable, right? Consider planet Earth as Earth Incorporated. Consider planet Earth as a business. What is its capital? What is its capital? The capital of planet Earth is natural resources, right? All the companies in this world are different department of one company called Earth Incorporated. Whichever company you take, some are processing raw materials, some are processing manufacturing finished goods. These are all different departments of one company called Earth Incorporated. What is the resource? What is its capital? Natural resources. 60% of natural resources have been destroyed in the last 400 years of industrialization. Right? These are non-renewable resources we are talking about. 60% of natural resources are destroyed in the last 400 years. Now, 400 years in the Earth life of a few billion years is just a microsecond, or probably less time. So it's a very short time. So since we have destroyed 60% of the natural resources in just 400 years, is this progress or is this regress? Are we progressing or are we regressing? This is a question asked in this book, by Dr. A.F. Schumacher way back in 1973. He had already visualized and seen the effects of automation at that point of time, even when there was hardly any automation. But he knew we were progressing towards it. And these are the questions which he had brought up in his book. According to him, man should have stopped at building tools. The day he started, he says, the day we start building machines, we are starting on a path of self-destruction. Now, whether this is true or not true, it's a matter of research. We have to find out. But apparently, today, all the problems which we are facing, like climate change, 600 species are getting extinct every year, forests are getting destroyed, we have floods, natural calamities. All these are results of man-made activities. So, according to him, he said we should have stopped at building tools. Okay, so this is a matter for research, philosophical aspect. But there is one thing which we can do and which I strongly feel about today. Petrol and diesel vehicles are getting replaced by electrical vehicles. Okay, electrical vehicles have much fewer moving parts than a typical automobile. For example, a typical car has more than 10,000 moving parts. An electric vehicle has around 37 to 50 moving parts. So much less. So what we can do is have a balance between automation and manpower. For example, in these electric vehicles, instead of automated manufacturing of vehicles, which is there, the vehicle companies can manufacture chassis, strong chassis with electric motors built into the hub. And the body is built by hand. There is a company called Lotus Engineering, if you heard of it. Lotus Engineering from UK is one of the best research companies for engines and developing racing cars in the world. Now, one of the first models of the car which the Lotus company had built was made of stainless steel, so it did not require painting because stainless steel doesn't rust. So they had built car out of stainless steel. Of course, it was a brushed stainless steel so that it doesn't become too reflective and glaring. But the beauty of that car was all the panels of the car were hand built and screwed into to make the body. Now, this is something which aligns with building tools, which Dr. Schumacher was referring to. We can build the main component, which is the chassis, and which is critical part safety required for the safety. That chassis can be built by car companies, and the bodies can be built by small companies which are maintainable by hand, manufactured by hand, maintainable by hand. So this could be a blend between automation and manpower. This is basically a philosophical outlook. Now we come to one of the last topics for today. Ultimate in robotics. In 1974, one message from Arecibo antenna was sent into space. It was directed at the globular cluster M13 at the edge of Milky Way galaxy in 74. Okay. It basically contained information about humans on Earth. That message, which was beamed into outer space by using a megawatt transmitter, it contained information about humans on Earth. Basically, what the message contained was this. It contained the numbering system which we are using for the message. It contained the atomic numbers like hydrogen, carbon, nitrogen, oxygen, and phosphorus which make up the DNA, the formula of compounds that make nucleotides, the number of DNA nucleotide human genome. So this kind of information, where the system originated, where these messages originated, from which planet, all these was put in that message. Now this message was 1679 bits arranged in a matrix of 23 by 73, which are prime numbers. Okay, and the message does not make meaning if it is put in any other way. So the reason for using prime numbers was the message could fit only in one way and it could be easy to decode. So that is why they use prime numbers for arranging this message. Okay. Now this was on the left hand side. We have two pictures here. On the left hand side is a message which was sent into space, and the second, this was sent in 1974. In 2001, a message appeared in a crop circle on a crop field outside Chilbolton Laboratory in UK. Now everybody is saying this is a hoax. Okay, this is a question for debate. I don't want to get into that whether it's a hoax or whether the actual reply was received. But what it brought out some interesting things. Okay, what was interesting was in the reply message which you received, the carbon atom was replaced with silicon atom. Okay, and the DNA, which is a double helix, this was shown, the human DNA was shown here on the left hand side of the picture, as you can see. It's a double helix spiral. On the right hand side, you can see the DNA when silicon was introduced. It's a different kind of it's a spiral of two different wavelengths or twists rather. Okay. Most important was carbon was replaced by silicon. Now we know silicon is used in semiconductor industry for manufacturing processors, memories, FPGAs, etc. Implanted inside human beings and connected to nerve receptors. Not just implanted inside humans, but the endings are connected to nerve receptors and they are triggering responses by sending messages to this chip. There is one UK professor who is doing this right now. Okay, so silicon chip is implanted inside human beings and it is connected to the nervous system in a very, very primitive way. Now, is it possible to integrate DNA? Is it possible to integrate silicon into human DNA and build you superhuman? Since silicon is used to make chips, processors, FPGAs, can they be integrated into the DNA? This is the ultimate field in robotics where a human being is transformed into a superhuman being using some DNA modification. Okay. So this basically ends our talk on robotics and automation. It's a brief idea, brief overview in different areas, about different areas which can be researched. Lastly, we'll come to one particular topic, which is the requirements for research. What are the requirements to conduct research in any field rather, especially in this field? Ability to zoom in from system level to element level and zoom out from element level. So we need to understand the system inside out. Basically, this says is we need to understand the system inside out. What is the importance? What is the implication of one particular or function of one particular element in the system? Suppose that element fails or it is changed, how it is going to affect the behavior of the system? Or we need to first understand what the system is expected to do and design the components into the system. So the ability to zoom in and zoom out is very, very important for research in any field. Today, at higher levels, we need not just your subject knowledge, we need knowledge of other fields also to do research. Whenever you talk of research, we need to understand the system in a better way. And we need knowledge of different subjects, especially robots and automation. Since robotics also deals with humans, we need to understand human psychology. We need to understand management principles. We need to understand operations. We need mathematics. We need statistics, probability among the core subjects. Okay, among the other subjects. Of course, to conduct research or get into research, you need basic qualifications and subject knowledge. That is the first. Besides that, you need knowledge of these other subjects also. Ability to have a broader view and perspective in scheme of things. Ability to design simple experiment to test hypotheses and derive repeatable results. Open mind to accept results without bias. Fit theory to result and not fit result to the theory. One of the important examples I can give of this is the Challenger, Space Shuttle Challenger disaster. Dr. Richard Feynman, the famous Nobel laureate, who is known as the father of nanotechnology today. In his book, Pleasure of Finding Things Out, says he's mentioned the case of Challenger disaster and how people even at NASA had closed minds. He's saying you need an open mind to accept the result. The result was so simple. Basically, Challenger accident happened because a gasket failed. A gasket which prevents leak of liquid oxygen, the liquid fuels, became brittle in cold weather and cracked. The morning this shuttle was launched, the weather was exceptionally cold. The temperature had dropped drastically. It was exceptionally cold, and there was a good chance that the gasket had cracked. This Dr. Feynman found out when he was in his friend's garage, and the friend was discussing a problem with gaskets. He was explaining to him how the gasket is flowing and the fuel pump used to get flooded with petrol, and he had problems during cold. Suddenly, Dr. Feynman realized the same thing must have happened with the Challenger. There are two big boosters, one containing solid fuel, one containing liquid fuel, and the solid and liquid fuel are mixed in a particular. When there is a controlled reaction, things are going fine. But if the gasket fails and there is an uncontrolled release of fuel, things could become, the whole mixture could explode, and that is what precisely happened. But this result was not acceptable to many scientists at NASA because they were not looking at the result without a bias. They had their own theories and their own thing. It was proven to them with experiments, finally. Many experiments were conducted and the experiment showed that this is precisely what happened. Even then, it was difficult for them to accept the result. So this, having an open mind to accept the result is very, very important. You cannot approach a problem with a fixed notion or fixed theory in your mind and then you find results which suit your theory. That should not be the way. You first find what the theory has to say or the experiments give you, and then find a theory which will fit all these results which you have seen. So this is a very, very important requirement for research. Objective approach. You have to leave the person out of it, obviously. You have to look at it from a third man's point of view. You should not allow your own thoughts and ideas to color the result or the theory. Thank you very much for the opportunity. I hope I was coherent and I was able to bring to you some ideas. This by no means covers everything. There are a lot more areas which are open and can be researched on, but this is at least some glimpse into what the research opportunities are in robotics and automation. Thank you all. I hope everything was clear.
Yes, sir. I request a participant, if anyone has any questions, please ask. Please unmute yourself and ask the question. Or else you can just put it in the chat box and we can later on send it to the sir, and we will directly discuss these topics and you will get your answers directly on your emails also. So anyone has any questions?
I hope it was not too theoretical.
No, sir, it's not. So I will just close this today's session then with a vote of thanks. So I would like to express my proud and heartfelt gratitude to our honorable guest, Mr. Sunil Gokhale, sir, for sparing us a time out of his busy schedule to address and guide and inspire us today with his inputs and insight. This session, we have learned a lot of things like need of robotics and automation, what are the different soft bot, what is the need of the capture, after that what are the different research areas area that we have in robotics and automation, what are the different human consideration and effects, what are the different developments that we are happening in the robotics and automation, and also what are the different requirements that we need for the research. So these are the things that many of the things that our Mr. Sunil Gokhale sir has completed. Now, this is our great privilege to have you to share this experience, your experience with us. I would like to extend my sincere thanks to the participant for making this session a wonderful session. Thank you so much, Sunil sir, for this wonderful session.
Thank you for the opportunity to present and talk to you people. Thank you very much, sir.
Thank you, sir. There is one announcement for the participant. Our next session will start at 1 p.m. of Dr. Rajesh Kumar from MNIT Jaipur. Thank you, everyone.
Thank you.
Sir. Thank you.
Yeah.